Do we all inhabit a vast emptiness? Given the vast diversity of the starry sky, what appears to be a contradiction can really help to unravel one of the biggest mysteries of contemporary space exploration. The so-called Hubble tension may be explained by the Earth's location in a type of underdense bubble in space, even though the measured value of the Hubble constant just does not fit our theoretical models. However, while this innovative method at last resolves the disparity in the measured values, it also immediately creates a new research conundrum. Such gaps in the universe really shouldn't exist based on what we know. Although it may appear straightforward at first, one of the biggest mysteries of modern study is the real rate of expansion of the universe. However, from the universe's creation, some 13.8 billion years ago, it has been expanding continuously, which is one of the fundamental facts of astronomy. To gain a better understanding, it is important to know that the universe is not currently expanding into an existing space. No, the thing that is constantly increasing is space itself. It should be mentioned that the speed at which the individual galaxies move apart as the universe expands is related to the distance between the galactic worlds. This implies that galaxy's distance from us increases twice as quickly if it is twice as far from Earth as galaxy B. However, in order to determine the precise rate at which two galaxies are moving apart, we need to know not only how far apart they are, but also a factor that can be used to multiply that distance. This is exactly where the Hubble constant, a parameter in Einstein's field equations, enters the picture. Despite its name, the constant is only constant in space and not in time. The appropriate value of the Hubble constant and, consequently, the current rate of expansion of the universe can be found in essentially two distinct ways. The cosmic background radiation, or the remnant of microwave radiation from the time immediately following the Big Bang that still permeates the whole universe today, could be used to assist determine it on the one hand. Therefore, scientists calculate the present expansion speed to be 67 chem/s per megaparsec by measuring cosmic background radiation and combining it with theoretical models of cosmic development. The main issue, though, is that the measured values of the Hubble constant are substantially greater and diverge greatly from the theoretical predictions. In other words, we are faced with a Hubble constant that unexpectedly equates to 73 chem/s per megaparsec if the distance measurement is based on supernova, red giants, gravitational lenses, and variable stars. At first sight, a 6 chem difference might not seem like much, but when we take into account that the expansion rate has increased from 244,000 chem/apes per megaparsec to 264,000 chem/a per megaparsec, this changes drastically. On the other hand, this just indicates that the universe is expanding at a rate of 20,000 chem/h faster than the cosmological standard model predicts. However, how can that be possible? Is the cosmos not what we think it is? The most straightforward explanation is that the astronomical devil of error has infiltrated. This suggests that we may have a research puzzle that isn't actually a puzzle at all because of a mix of measuring errors and inaccuracies in the past. Adam Rees and his colleagues verified this by analyzing more than 320 Cepheid variables in many galaxies with the James Webb Telescope, many of which had also been previously analyzed by the Hubble Space Telescope. The American who discovered the accelerated expansion of the universe through distant supernovae in 2011 won the Nobel Prize in Physics. So if anyone knows anything about this subject, it's Adam Rees. But in the case of the latest study, Rees had a different idea. Webb ought to reaffirm the Hubble tension. Additionally, the Hubble constant in the new data is far higher than the one found in the theoretically calculated models. Luckily, Rees also saw a solution for this perplexing departure right away. Perhaps we have just misinterpreted the universe. An unidentified force that has not been considered in the cosmological standard model may be something we have missed in our comprehension of the universe. This can be an incorrect understanding of gravity or a new kind of particle. Additionally, it is possible that there is an exotic type of dark matter or dark energy that we are now unaware of. To refresh your memory, there has been no direct detection of dark matter or dark energy to date. As a result, where Einstein's theories fall short, completely speculative forms of matter and energy were proposed to explain both the accelerated expansion of the universe and the motion of visible matter. Another team thinks they have finally figured out the intriguing mystery of the Hubble constant, while Adam Reyes freely alludes to the potential ignorance of the astronomical study community. The following succinctly describes the study that presented the unique answer, which was published in the Royal Astronomical Society's monthly notices journal. We inhabit a huge empty place. What does that signify, though? The starry sky isn't exactly empty, after all, with its millions and thousands of things. The idea that our Earth is situated in an area of space with comparatively little matter is what is intended, not a night sky devoid of stars. The cosmic emptiness is likened to an air bubble in a cake in the news release that the worldwide research team issued for their work. For example, the gravitational forces in the sparsely populated bubble move the galaxies inside it toward the edge of the void, and quicker than would be predicted because the density of matter outside the bubble is correspondingly higher. This would explain why the universe appears to expand more quickly close to us, or up to roughly 3 billion light-years away, than it does farther away. Therefore, this contradiction to the mainstream model of cosmology can be resolved by the existence of regions with below-average density. Unfortunately, though, it also brings up an entirely separate issue. Since matter in the cosmos should be dispersed uniformly, such underdensities should not exist at all, and the standard model does not account for them at all. However, there is a method to circumvent this new contradiction as well, but it necessitates abandoning Einstein's theory of gravity. This suggests that gravitational forces might end up acting differently than Einstein anticipated. This theory has actually existed for a while. The researchers used a modified theory of gravity, first put forth by Israeli physicist Mordechai Milgrom in 1983, as the basis for their investigation. By altering the equations of motion of matter in the gravitational field, the so-called modified Newtonian dynamics, MOND, explains the rotational behavior of galaxies. As a result, this theory is also regarded as a dark matter substitute, yet it remains a contentious topic and has not yet progressed past the level of an outsider theory. Nevertheless, MOND correctly predicts the presence of underdense bubbles in space, and this is the key finding for the study's authors. One of the biggest mysteries in cosmology would have been resolved if gravity truly behaved as Milgrom predicted, with the Hubble tension issue having vanished moment by moment. Or is there really no Hubble tension? If Wendy Friedman is right, we might wind up dealing with issues that don't actually exist in spite of all the fresh research and observations. We must briefly revisit Adam Reyes's research work in order to comprehend what is meant by this. According to the Canadian astronomer, Cepheid variable brightness measurements may be significantly distorted by dust, gas, and the influence of neighboring stars. This is due to the fact that Cepheids are mainly found in galaxy disks, where stars can occasionally be so near to one another that their light overlaps. Friedman and her team used the James Webb Telescope to study 10 neighboring galaxies, which include 2 additional distance markers in addition to Cepheids, so that a distant observer might test their idea. On the one hand, red giants are on the verge of igniting their cores with helium. The heavenly bodies at this point achieve an inherent brilliance that is mostly unaffected by their makeup and past events. Therefore, inferences on their distance can be made by comparing them to the apparent brightness. For the other stars under investigation, which are more developed and carbon-enriched, the circumstances are rather similar. After a number of years of study, the results showed that the distances measured with the 2 new approaches are in very excellent agreement with one another, and that they all produce higher distances than those based on Cepheids. Therefore, it is possible that the Hubble tension is actually caused by our miscalibration of the cosmic distance ladder. In particular, the lowest rungs of the distance ladder are identified using Cepheids. The value of the Hubble constant will unavoidably be skewed, though, if the lowest rung already has a systematic inaccuracy that subsequently passes through every succeeding rung. But as of right now, neither the precise location of these faults nor their existence are known. Adam Reyes actually highlights that the Webb data he has gathered specifically excludes the likelihood that systematic measurement errors or imperfections brought on by nearby stars' light have had a major factor. However, you can now take on the pivotal position of a brand new subscriber. To ensure that you don't miss any more of our videos, please click the thumbs up and subscribe buttons.